Thank you very much for coming, and I'd like to talk about Iceland today once more, but today I'd like to talk about Iceland in its entirety and about the origin of Iceland, not just about the recent eruptions, but I'm going to introduce some concepts about how Iceland formed, why it is where it is, and how it all came about. And then I'm going to introduce you to the Champions League of Icelandic volcanoes. And then we're going to talk a little bit about the pros and cons of volcanoes as well. What is good and what is not so good about volcanoes. Because like everything, there's good sides and there's bad sides about volcanoes. So I call it the journey from the center of the Earth, not to the center of the Earth, as Jules Verne called it, because magma obviously rises from the interior upwards. And it's a probe for us geochemists and geologists to look into the interior of the Earth. So where are we? Well, we're pretty high up on the globe, and this is where Iceland is, and we are just about here, close to the Faroe Islands right now. We're just outside this red box here. And, well, Iceland is an intriguing place because it combines ice and fire. So here we have these two components that make Iceland so special. And Iceland sits on a mid-oceanic ridge, and in particular the mid-Atlantic ridge. This is where the Atlantic spreads, and it spreads on a continuous basis. It spreads every day just a tiny little bit, and this ridge actually spans all around the globe, and it's about 60,000 kilometers of volcanic ridge, and most volcanism on the whole planet happens along these ridges. 84% of all volcanic activity is submarine along these mid-oceanic ridges. So Iceland is in the heart of this spreading zone, this mid-Atlantic spreading zone, and we can see the spreading zone here, and it continues to the north as well. And Iceland sits right on top of that, and of course this means we can see the spreading zone on land in Iceland, and this is the Reykjanes Peninsula, and it moves via a complicated network of spreading zones all through the center of Iceland. And here you can see the plate boundary between, well, the North American plate and the Eurasian plate on either side of it. And the spreading is, well, it's about 2 centimeters a year. And I usually tell my students, that's about the speed with which your fingernails grow. So this is how fast the Atlantic spreads. The Pacific is a much older ocean. It spreads a lot faster. It spreads at 7 centimeters a year. That's about the speed with which your hair grows. So you can get a sense for that. So here we have the oldest rocks in Iceland, and they are here at the fringes in the very east and the very west. And this is where we had a port day just before we sailed off towards the east. And Iceland's oldest rocks are geologically very young. They're only about 12, maybe 14 million years old. And when we think of rocks in Sweden or Norway, which are thousands of millions of years old, the rocks in Iceland are extremely young. So, but here's one of these questions that I find personally very intriguing, and that is, well, we have these long segments of oceanic rift zones. They go through the Atlantic and through virtually all the other oceans as well, but only on Iceland do we actually see them above the water level. So what's so special about Iceland? Well, and I hinted at this yesterday if you were here, the thing is that Iceland is not just a spreading ridge, it's not just a plate boundary, there's something else going on. And we call it a plume, a mantle plume, or some people call it a hotspot. This is very similar to what we have under Hawaii, but also many other places, like the Canary Islands, the Azores. There we have an anomaly that comes from deep inside the Earth, and it rises up, and it just happens to coincide with this oceanic spreading ridge, and that makes Iceland so unique, so special. So here we have a spreading ridge that is hit by one of these deep-seated mantle plumes. And Well, these spreading ridges, they usually start off somewhere in the continent, and we have one like this. It's the Rift Valley in East Africa. It looks like this. We don't have an ocean there yet, but the plates are spreading apart, and once they have spread to a sufficient degree, we actually start having water flooding in, and then eventually we make a large ocean with a ridge in the middle. But here you see Iceland in the middle of the Atlantic Ocean. Here's Greenland. Here is the British Isles. And here is Iceland along the ridge. And it sits here, and there's a swell of ocean rocks underneath, and it continues all the way to Greenland and to the British Isles. And there we have volcanic rocks that are very, very similar to the ones on Iceland, only they're much older. So this Icelandic plume was there for a long time. It must have been there since the beginning of the Atlantic Ocean. And the rocks are present here in East Greenland, as well as in the Hebrides and in Northern Ireland. So we have initially a plume that came up, and it hit the areas here in Greenland when the Atlantic was still together, and at the same time here in the British Isles. And then the Atlantic started to spread, but the Icelandic plume maintained its position. It was strong for many millions of years since the Atlantic started to form, and it's still going strong at the present day. So, having talked about this, well, people have reconstructed how this concept of plumes work, and the first person who really thought about mantle plume was actually Athanasius Kircher in the 1670s, and here's his drawing. He believed that there was a fire inside the earth and it would rise up and make volcanoes here. It was heavily disputed at the time, and a lot of people didn't believe him. But today we're looking at it in this way, and actually he wasn't so far off. I'm actually quite impressed with his thinking. And this is a reconstruction. This is the present day. This is 30 million years ago, 60 million years ago, and this is 90 million years, 120 million years ago, and this is about 150 million years ago. And when we start there, this is about when the Atlantic started to form. There was two of those plumes, one of them the Icelandic plume, and one probably sitting somewhere under Greenland. And eventually these two merged, and they give rise to the present-day Iceland plume, and it's still going strong to the present day. And for all we can tell, it'll continue to do so for quite some time in the future. So where do these plumes come from? Well, we really actually know only a little bit about them. It's very complicated, but we know that there are subduction zones, for example, in the Cascades in the US, but also in Japan and Indonesia, and their material is pushed down into the mantle, and we can image this material sinking all the way down. And once it rests there for some time, we believe that it heats up from radioactive decay, and then it might actually rise up again. These are very long processes. They take thousands of millions of years, and we believe that these plumes come from very deep, from what we call the lithosphere graveyard, down here at the core mantle boundary. But of course, nobody has ever been there apart from Jules Verne, and therefore we are speculating, I have to admit, but the chemistry of the magmas coming up, they tell us that something like this must be happening. So we believe that these plumes come from ancient, lost continents that are long, long gone. We don't see them at the surface anymore, but remnants of them may still be present deep within the earth. So when we move this material up now, then this plume hits this area where we have Iceland at the surface, and here's a reconstruction from a depth of about 500 kilometers, and this is a very simplified sketch of it. The center is believed to be sitting right under the middle of Iceland, and in reality it's a bit more complicated, but here's the surface expression, and it seems to have a narrow stem in the middle, but it's a bit of a wider zone that is affected, and this wider zone initially, as I said, was causing some volcanic activity in Greenland and the British Isles, but now it seems to be very narrow, focused almost exclusively on Iceland. So when this magma then rises up, the plume material spreads out, and eventually it starts to make magma reservoirs in the crust. And this is now very close to the surface. There we're producing magma chambers. And, well, chamber is one of these terms. It's not in fashion anymore. We call them now magma reservoirs, because chambers are empty, and magma chambers shouldn't be empty. They should contain magma. So magma reservoirs. And then we have all these ascent paths, the conduits, and depending on what their orientation is, we have different names for them, sills and dikes and etc. And eventually they feed volcanoes at the surface. But we must be aware only a fraction of the magma ever reaches the surface. Most of it gets arrested inside these islands, inside Iceland, and actually the uplift of Iceland is stronger than the volcanic production. So there is probably at least 50 to 70% of magma that is never reaching the surface, but is actually emplaced inside the island itself. So this now leads to this strange interaction between the fissure zone, the rift zone that we see at the surface, and all the way down into the southern Atlantic and, of course, into the northern Atlantic. And this area is where most of the volcanoes are, and this is where we believe this plume just hits this oceanic ridge, giving rise to some 30 larger volcanic systems. And here's a list of all the important volcanoes, all the Champion League players in the Volcano League. And we don't have to go through all of them. I'll just introduce you to some of them. Some of them have very complicated names. Others are a little easier to pronounce. But my goal is now to give you the most important ones and a little history to each of them. So before we do that, I should point out there's two core types, and this is central volcanoes. These are usually the cone-shaped volcanic edifices, the stratovolcanoes. And in Iceland, because of this rift system, we have fissure volcanoes. These are volcanoes that form along cracks in the earth crust, and they behave a little differently. They're not less dangerous, they're just different. So, and before we plunge into our Volcano Champion League, here I should point out each of the volcanoes has a slightly different character. There is no volcano that's exactly the same as another one, like humans, and they come with different hazards. There's proximal, distal, and temporally extensive hazards. Some of the features happen on the scale of hours, some take days, weeks, and others, like climatic effects, take years. The local effects are usually lava flows, but also ash clouds and landslides, pyroclastic flows, hot ash clouds, and then also mud flows. And these features, they are usually happening on the scale of hours to days. Sometimes they take weeks, while these climate effects, like changes of weather, for example, they often take years, and they can be detected several years after a large eruption.